In this example problem, we're going to try to put together some of the ideas that we've learned in the lecture and the tutorial sequence this week. Read the example provided on the website. It deals with atherosclerosis, which is also called hardening of the arteries. Essentially, what was done in this study was that these authors examined the impact of a 16-week physical activity program on LDL cholesterol resistance to oxidation in 16 healthy young adults. So they measured, after these adults completed the 16-week program, they measured their oxidation rates, and they found that in this population, they observed a mean oxidation rate of 8.2 micromoles per minutes per grams, and they found that the standard deviation was 2.5. Throughout this example, we're going to assume that these oxidation rates are normally distributed. And we're going to try to make inference about the efficacy of this 16-week physical activity program using data from our sample of 17 healthy young adults. First thing we want to ask is, what's the distribution of the sample mean for these healthy young adults? Let's denote our sample mean x bar. And we saw before that x bar is equal to 8.2. with sample standard deviation equal to 2.5. Now we're assuming that x was normally distributed, where x is one of the measurements for oxidation rates in one of these participants. And therefore, we do know in statistics, we know that if x is normally distributed, we know that x bar is also going to be normally distributed. However, because we don't know mu and sigma squared here, and because we have a small sample size, we can't directly use the central limit theorem, so we really don't directly know the sampling distribution of the mean. However, given that we know that x is normally distributed and we know the sample standard deviation, we do know, we learned in class this week, that x bar minus the true mean mu divided by s, the sample standard deviation, over the square root of n, is going to follow a t-distribution with n minus 1 degrees of freedom. So in our case, n minus 1, 17 minus 1, is going to be 16. So we don't know the direct sampling distribution of x bar, but we do know that x bar minus mu over s over the square root of n follows a t-distribution with 16 degrees of freedom. Now this has been a lot of talk about sampling distributions and the mean. Let's try to put it all together and try to think about what do we do when we're looking at hypothesis testing or even constructing confidence intervals. So I've laid out a few scenarios here. Let's consider a sample where we know sigma, we know the true standard deviation in the population, and we have a large sample size. Well, in this scenario, we can just use the central limit theorem to know that we can then use a one-sample z-test and just use properties of the normal distribution. On the other hand, if we know the sample standard deviation, and let's say we don't have a huge sample size, but we had normally distributed data, then we just know, because we started out with normally distributed data, we know the standard deviation, we then know that our sample mean is going to be normally distributed, and then again, you can just use normality and make all of your inferences using this one-sampled z-test based on the normal distribution. So in this setting, you end up with a test statistic that looks like x bar minus mu divided by sigma over the square root of n. And that guy is going to be normally distributed, standard normal distribution. Now the setting that we're in a lot of the times when we have continuous data is when we have sigma unknown, but we can make a normality assumption. So in this case, we know that we can then use the t-distribution. And again, we saw that t, which is equal to x bar minus mu divided by s over the square root of n, is then going to follow a t-distribution with n minus 1 degrees of freedom. So hopefully this sort of clarifies the different scenarios that you can end up in, and you can figure out then what test you should do. Now let's go ahead and do an example. So suppose that the average maximum oxidation rate in the population of healthy young adults who did not complete the program was 11.3 micromoles per minutes per gram, and the standard deviation was 2.3. Now we're going to look at the predictive intervals. Recall what a predictive interval was. We're going to look at a 99% predictive interval for the sample mean maximum oxidation rate from a sample of size 17. So recall, what we're doing in this case is, let's say we have these healthy young adults. Let's denote Y as the observation of maximum oxidation rate for a healthy young adult who did not complete the program. Y is normally distributed with mean equal to 11.3 and sample standard deviation of 2.3. So variance is 2.3 squared. Recall that if you want to construct a predictive interval for, let's call this x bar 0, from a sample of size 17, a predictive interval looks like mu plus or minus this z distribution, the cutoff, where 99.5% of the mass of the normal distribution is in the lower tail of that guy, times sigma over the square root of n. Now open up Stata and we'll work through that calculation together. To construct our predictive interval in Stata, we would type display mu minus inverse normal 0.995 times my standard deviation of 2.3 divided by the square root of n, which is 17. We obtain a lower bound. Changing the minus to a plus, we obtain an upper bound, and we find that a 99% predictive interval for the sample mean from a population who did not complete the physical activity program is about 9.9 to 12.7. Now recall that when we looked at this population who did complete the physical activity program, their sample mean was actually equal to 8.2. So we can look and we see that x bar does not lie in this predictive interval. So this sort of is maybe a first suggestion for us that because x bar doesn't lie in the predictive interval for the adults who did not complete the program, it looks like the mean among adults who did complete the program might be different than those who did not complete the program. So again, thinking about these healthy young adults who completed the program, now we're going to try to look at a 99% confidence interval for the mean oxidation rate in those adults who completed the program using our sample of 19 participants. Recall that a 99% confidence interval for the mean is going to be equal to x bar plus or minus this z cutoff times sigma over the square root of n, when sigma is known. However, we don't know sigma in this population of healthy young adults who completed that program, so it's not reasonable to use this confidence interval. Instead, we should look at x bar plus or minus the t distribution with 16 degrees of freedom, using that cutoff, times the sample standard deviation over the square root of n. Open up Stata and we'll do that calculation. To construct our confidence interval within Stata, we can go Statistics, Summaries, Tables, and Tests, and then we can go to Confidence Intervals. We're assuming normality here, but remember we don't actually have any data read in. So we can't directly use confidence intervals. Instead, we need to go to the confidence interval calculator. So the normal CI calculator, our sample size is equal to 17. Remember, our sample mean is equal to 8.2, and the sample standard deviation is equal to 2.5. And we want to change our confidence level now. We're looking at a 99% confidence interval. Hit submit, and we find a 99% confidence interval for the mean. You can see that it's supposed to lie between about 6.4 and about 10.0. So repeatedly sampling from this population, we would expect the mean for the population of healthy young adults who completed the program to lie in this interval about 99% of the time. Now we've calculated this confidence interval using the t-distribution. An interesting question is, what if instead we decided to calculate the confidence interval using the z-distribution? Where we were willing to make the assumption that the standard deviation was known and was equal to the standard deviation in the population who did not complete the program, which we saw before, was 2.3. Now, in this scenario, would your confidence interval be wider or narrower when we constructed our confidence interval with sigma known? So let's think about that. We have this confidence interval here where we assume sigma is known, or we have this guy that we used based on the t-distribution, So in this scenario, how can we assess this problem? Well, we know in this case that this is always going to be true, that the z distribution quantile is always going to be less than that comes from the t distribution. Therefore, your interval based on the t distribution will always be wider if sigma and s are the same. In this case, we also see that sigma is less than s. So we know that in this example, the interval based on the t distribution will always be wider. However, this won't always be the case. We know that this relationship always holds, but given that s, there's some stochastic variability in here, there's random variability, so this may not always be the case. So if by some chance you ended up with a sample standard deviation that was less than the true population standard deviation, you could end up in a scenario where your confidence interval based on the t distribution was narrower than that based on the z distribution. But typically in practice, your confidence intervals based on the t distribution will be more conservative and they will be wider. That is not always the case though. The last thing we want to look at in this example is we want to test the hypothesis that the mean oxidation rates in the healthy young adults who completed the program are different than the mean oxidation rates in the adults who did not complete the program. So to formalize this, first remember we have to pick a test. Since we don't know the standard deviation, we're going to use a one sample t-test. And then we state our null and alternative hypothesis. If mu is the mean oxidation rate in healthy young adults who participate in the program, we're going to test the hypothesis that mu is equal to 11.3, which was the mean in those who didn't complete the program, against the alternative that mu is not equal to 11.3. Okay, so now we can go ahead and do that test with Instadata. Our sample size is 17, sample mean is 8.2, sample standard deviation, remember, was 2.5, and the hypothesized mean is 11.3, and our confidence level is 99% in this example. And we hit submit. Now, as a statistician, you should never jump straight to the p-value. When you're presenting the results of a test, you want to make sure that you tell a story. So if I were telling the story in this case, I would say that using a one sample t-test, I obtained a test statistic of negative 5.11, which under the null hypothesis follows a t-distribution with 16 degrees of freedom. This corresponds to a p-value of 0.0001, and therefore, at the alpha equals 0.01 level, I know that p is less than 0.01, and consequently, I would reject the null hypothesis. Again, I would never just stop there, though. Just saying that you reject the null hypothesis does not complete the story. Instead, what I would want to say is that using this sample of 17 healthy young adults, the data suggests that this 16-week physical activity program lowers the maximum oxidation rate in healthy young adults. We have evidence that this oxidation rate is less than 11.3 in our population of healthy young adults.